Morning. Welcome to 21st Century Modern Architecture. My name is Shaun and what we're going to talk you through today is 3 demos in 30 minutes. How to scale internet services. And to do that, we've been sitting down for 2 hours, we've been through Keynote. This is the builders track. How about we build something? So we're going to kick off straight away with a demo. And it's a crowd participation demo. So I'm going to hand over to my colleague Gabe, and he's going to take you through it.
Thanks, Shaun. Hey, guys. Welcome to the track. We got a lot of cool demos today. I'm going to go pretty quick because I want to make sure to save time for the other demos we're going to show you. But before we get into it, I have a question for you. Why are we always smiling in selfies? I mean, the range of human emotions and experience is a lot more varied than just happiness. Sometimes we're sad. Sometimes we're angry. Sometimes we're confused. Sometimes we're just calm. So as we get into this demo, I want to do a little experiment. Let's pretend I work for some big photo company, and my company wants to run an online contest where I encourage people to take selfies with a wide variety of emotions. And I want to give out awards to, the people who give the best selfies showing different emotions, not just smiling all the time. And so what if I did make that? And what if I publish this online and maybe, oh crap, we made the front page. Maybe it's Reddit, maybe it's Hacker News, something like that. Can we handle the load? Is the online submission system we've built to take selfies in and rank them and show the results going to be able to scale to meet that load? Well, I don't work for a large photo company. I work for AWS. But we can simulate such a contest here today. And so I want to introduce you to the Awesome Selfie Challenge. So get your phones ready, because in a second, I'm going to ask you guys to all take out your phones, scan a QR code, or just load a URL, take a selfie of yourselves, and then we'll go ahead and see who wins. Now, to encourage you all to participate, besides the fact that it's just fun to take selfies and see yourself on screen, I'm going to give $100 in AWS credit to each of the category winners. So here's your phones. There's the code. Remember, you might need to zoom in to get that QR code scanned by your phone, or just go ahead and type in the URL there. Now, I know what you're thinking, maybe. How are we going to decide who the winners are, right? Is it going to be me? Well, that's not very fair. I'm subjective. I'm just a human. So let's take subjectivity out of it. And instead, I'm going to use Amazon's Recognition. It's one of our AI application level services. And one of the features that it can do is it can scan faces and look for emotional content within them. So it'll rank them into different categories, like happy or sad or confused or disgusted, angry, etc. And so we're going to let Recognition decide who's got the best selfie in each category. And so if you end up on screen, after this talk is over, if you come see me, I'll just hang out by the front here for a little bit. I'll go ahead and I'll give you $100 in AWS credit to use for whatever you want. So you'll just give me your email, and I'll follow up with you personally later and give you that code. OK. Can I just get a show of hands if you were able to upload a selfie successfully? I just want to see that we've got some participation through the 3G and stuff. That's good. Thank you. I'm going to give it just another minute here. I'm just going to see how we're doing. Good. OK. And one of the other things I mentioned was that Recognition is going to scan all the images, but it's going to do more than just that. It's going to check to make sure that the content that people are uploading is actually legit. And so I just went through and did a double check to make sure all the pictures I'm about to put on screen are acceptable for public display. They are. And so I'm just in the process of submitting that right now, and we should be good to go. So hang on a second. Shaun should be able to refresh the results page, and we've got some winners. That looks good. OK, so let's go to the results. And now we'll go to the demo computer here so we can see those faces. So congratulations to these people. There's those are the winners. If you see yourself up there, please come see me afterwards, and we'll go ahead and get you the credit. And thank you for participating. So let's move on. How did I build this? So I'll go back to the slides now. Thank you. How did I build this? Well, it was actually really easy. This is the architecture for it. I started with AWS Mobile Hub, which makes it easy to get started building applications for mobile devices. In this case, this was just a simple web app powered by React. And Mobile Hub set that up for me. It also set up a Cognito user pool and a CloudFront distribution backed by S3. And so what happens is, when you load up the app, you get a set of temporary credentials delivered to your to your device via Cognito. And those credentials give you access to an IAM role that will let you upload a file to an S3 bucket. When those images get into the S3 bucket, they need to be processed. And so a series of lambdas kick off, and they're orchestrated by one of our services called step functions. If you haven't heard of step functions before, they just let you coordinate how data flow can be processed by lambdas. So one lambda looks and computes the metadata information, the width and the height of the images. A different lambda passes it through recognition to say, is this image safe for public display? Does content moderation? Another one does the emotional analysis. Then all that data gets funneled into a table in DynamoDB. Now, because I've done a lot of web development in my past, I've built REST web services for a long time. I'm now a fan of GraphQL. I think it's really great. And so I was excited to be able to use one of our newer services, AWS AppSync, in order to get at that DynamoDB table. So if you haven't heard of it, AppSync is a service that lets you have a managed GraphQL endpoint to access data backed by Elasticsearch or DynamoDB or Lambda functions. It's really neat. So that's the architecture. Now, the one key takeaway from this is you'll notice there's no servers here, right? Everything here is managed by AWS, so I know it can scale to handle the load, and I don't need to worry about that. That's a theme I think you're going to hear a lot today. Is serverless is how you should be thinking about building apps, and serverless is more than just Lambda, right? It's anything you don't have to manage that will handle scale. And so that's it for the architecture, but one last thing I want to mention about this is you don't have to take my word for it. This was just a simulation today. FINRA, I think you heard at the keynote this morning, processes 500 billion validations of market events in the US stock market every day using Lambda. So it's insanely scalable, and it can definitely handle your loads. So now I want to move on, and I want to talk about internet scale services. Now, as you all know, internet scale services should be secure, reliable, and performant. We all know that, but security is about more than just passwords. Reliability is about more than just redundancy, and performance is about more than just scalability. So I'm going to talk about each of these three in turn, and I'm going to go pretty quick because, again, I want to save content for the other demos that are really exciting. So first, security. Security is job zero. We say that at AWS a lot. The first thing, and you heard about this in the keynote this morning as well, is ubiquitous encryption. Now, this is really just a concept describing a best practice in the industry, and you should definitely be encrypting too, whether it's terminating SSL endpoints with API Gateway, or encrypting your data at rest in S3 or DynamoDB or Aurora, or using KMS to manage your keys. AWS has you covered. What you might not know is that AWS is recently FIPS 140-2 certified, and that's a new certification for us that means we pass government-grade security standards for cryptographic modules. So I know that's going to make a lot of security-sensitive customers happy. Next, we've got a service called Trusted Advisor. Now, Trusted Advisor, you also heard about this morning in the keynote. It's a service that will scan your AWS environment and look for suggestions on how to improve your security and save costs. And I'll show you a screenshot of that in a minute. Finally, we have CloudTrail. CloudTrail is a service that will tell you what changed in your AWS environment, when, and who did it. And so that's anytime any API calls happen on your AWS environment, it's getting logged in CloudTrail. And it can ship those logs to an S3 bucket for additional peace of mind that you're keeping the logs in a safe place. So LG Electronics is one of our customers. They use AWS to enhance the service quality for 40 million LG smart TVs around the world. And they managed to save 40% in the process as well. So, of course, they're using a lot of our security features to do that. And so not only are they saving money, but they're doing it securely. As promised, here's a screenshot of what Trusted Advisor looks like. You can see that there's actually a number of different sections to the dashboard. This is the security section, and it gives me a list of things I might want to look at. In this particular example, it's telling me things like, oh, I need a password policy on my IAM accounts to make sure they have secure passwords, etc. Moving on. Reliability, right? Reliability is important. And I think it actually starts with knowing that the environments you're provisioning are repeatable, right? CloudFormation is our tooling that lets you set up infrastructure as code. CloudFormation is great. Something along with CloudFormation, especially if you're into serverless, is SAM. That's the Serverless Application Module. It's an extension for CloudFormation. And if you haven't heard of that, you should look up online because it'll make setting up serverless cloud formation stacks that used to look really verbose and about this many lines, about this many. So it's definitely something you should look into. Now, something that you didn't really hear a lot of in this morning's keynote that I think is really exciting is CodeStar. CodeStar is our service that makes it easy to get started with development best practices, whether it's setting up a Git repository in AWS Code Commit or connecting to GitHub. CodeStar will set you up with the process of having a CI/CD, continuous integration, continuous delivery pipeline with fast deployments, all managed for you in a few clicks. It's how I start all my projects in CodeStar, and I think it's worth looking at too, because it's important not only to have reliable infrastructure, but also a reliable development and deployment process. Finally, this one is about redundancy. We have a third availability zone recently added to Singapore. If you didn't know that, it's good to know. It'll let you run quorum services like Kafka or Cassandra on your own. Of course, we also use it for Amazon Aurora, our fastest growing database service, to make sure your data is well protected and highly available. Singapore Post was one of our customers that managed to expand into an entirely new region in a single day because they were using CloudFormation. Finally, here's a screenshot of CodeStar in action. This is the dashboard you get after you set up a CodeStar project out of the box. It'll tell you things like what your application activity is looking like, recent code commits, and even on the right-hand side, you can see there's a build pipeline that was set up automatically for us. And it'll tell you the status of after you commit code, when it gets built, and how it gets deployed. Finally, performance. So DynamoDB. I'm sure you all know about that, but if you need to take your DynamoDB queries and take them from milliseconds, which is already very fast, down to microseconds, DynamoDB Accelerator is a caching service you can put in front of DynamoDB to achieve really fast reads and writes. Another service is called Lambda@Edge. You can use Lambda@Edge to wrap CloudFront requests and responses to do things like intelligently pick better images to deliver to the client's device based on the device properties, or maybe doing A/B testing and taking that load off your server for figuring out what A/B tests to run for a customer. So you can read cookies, redirect requests, write cookies back to the customer. So it's good for A/B tests. Finally, X-Ray. So if you are building serverless distributed applications, then you're going to need a way to trace those requests as they go through different services that build up, whatever you're powering. X-Ray is a distributed tracing application. A distributed application tracing framework that AWS has built with a few simple API calls from whatever app service you're building. You can send data to X-Ray. I've got a screenshot of what this looks like in a second. TravelX is a company that uses Lambda@Edge. They're a customer of ours also. They use Lambda@Edge to make sure appropriate HTTP headers are in place for all of their API requests. For the responses to all their API requests. So that way, each developer doesn't have to remember to put a set of important headers on all of their responses. They push that responsibility out to the edge and let Lambda take care of it. Here's the screenshot of X-Ray in action. So you can see this is what a distributed application trace looks like, where different time is spent in different subcomponents that manage a particular request, and maybe where certain hotspots are. And so X-Ray makes it easy to see that stuff at a glance with a nice dashboard too. And now I'm going to hand it off to Shaun, who's going to continue telling you more about what's driving all this software.
Thanks, Gabe. So, we did the selfie demo this morning. We talked about a lot of different services, such as DynamoDB Accelerator, some of the services that we've been building at AWS, like AppSync. But really, why are we actually building this software? Why is open source community going out and building these different types of software? And so if you look at the journey and the digital access to date, it's actually the consumers that is driving what we have to change in software, what we have to change as builders. We've started in mainframes with dumb terminals and green screens. And then we've moved into the desktop era with our GUIs, and these were heavy desktop applications. We then moved into the web and started building everything in the browser. And things like PHP became very popular, so server-side rendering. And then finally, especially in Southeast Asia, into mobile. And in a lot of Southeast Asia countries where we don't have fixed-line internet, we've gone and adopted mobile much more than some of the other Western countries. There are 400 million middle-class Southeast Asians, and just about all of them use their mobile for a daily transaction. And so that has driven a huge explosion in data and the different ways that we have to write systems. Because if you think about scalability 15 years ago, you were doing ERP systems and payroll systems for big companies, and you knew exactly how many employees you had. You knew that you had 10,000 employees, and that was the highest scale, so you could measure your infrastructure. And now when we're doing mobile, we don't know how many people are going to use our infrastructure. And so it's variable. And so we have to build systems that can handle these kind of peak loads. And if you look at the technology drivers, it's not just the consumers that are creating this data. We now have billions of devices coming online through the Internet of Things, from cars to fridges to your watches. And they're not doing 1.5 gig a day of data, which is actually the average that a human generates on their mobile phone. They're doing petabytes and terabytes if you're talking about things like smart factories. The other big change that we've seen in technology is the compute power. So by adding cores, by moving into things like GPUs, we have been able to take technology that we invented 30 years ago, like machine learning and deep learning, and apply them to problems that we have to these huge data sources. And now that we have these massive swathes of data, we have to think about the way we store it and the way we query it, because it's greater than what a normal relational database can handle. And so we've had to go out and build completely different systems. And we've gone from having single node servers to having clustered servers. From things like Cassandra to Hadoop, from MongoDB to Neo4j, we've had to build completely different storage systems to be able to handle all of this data. Because the users moving into mobile has meant that we needed to query millions of things per second instead of thousands of things per second. We've moved into multi-data center architectures. And the problem with this is the infrastructure. You have to build all of this infrastructure and maintain it and understand what happens. If you have a multi-data center Cassandra, if you have Hadoop running over thousands of nodes, what happens if the master fails? How do you actually recover from the job? And so now that business wants more access, we have data analysts who want to query all this data. It's not IT people anymore who want to access it. We need to find ways that makes it simple for them, where they don't need people to actually write a whole bunch of code to stand up this infrastructure for them, or to order servers and wait 12 weeks. And so with that in mind, I'm going to show you another demo now, which is going to try and solve some of these problems. Okay, I'll kick the demo off and then we'll talk through it. Oh, or not. Who likes Python? Python 3, good times. Okay, so what we're actually doing here is we are creating a bunch of Lambda functions, and we are zipping them up, and we are uploading them up into North Virginia, so one of our regions. And we are actually taking about 25 gig worth of data. So it's actually data which is taking logs from mobile devices, and we are aggregating RAD revenue based on these users and which of these IPs actually hit our service. And so what you're seeing here and what actually we were doing at the top is the upload. So this is actually using the local internet. And you'll see here the 20 seconds, so 20.52 down the bottom, using Gnomon to time it out. So that's actually our upload. So this is with all your guys' mobiles and the Wi-Fi in here, me uploading those Lambda functions. Then what we're doing is we're building mappers. So we're going to do MapReduce over this architecture, and we're actually going to use Lambda to build the mappers and the reducers. So you'll see here I've got the mapper output. The one is they're using one key, and they're actually taking that data that I have, the 25 gig that's built into 202 keys, and they're actually splitting it out. So Lambda is processing one each. And the number that you see next to it, which is the 3.2, 3.4, and a couple of smaller files up the top, 0.46, this is actually the time that Lambda is running. So it is taking 3 seconds to produce each key. So we have a 20-second upload, but the actual processing time is only 3 seconds. And we see that we have 202 mappers. I've actually written the code so that it splits it out so that we can do one Lambda per mapper. So currently you can do that up to 1,000 keys in a normal account. And then down the bottom, I've also calculated the cost based on the North Virginia pricing. So we can see the total runtime, we can see the actual cost of storing it on S3, the running of Lambda, so we actually did 864 seconds of Lambda. And the total cost was 22 cents, and we processed 154 million rows of data. So without the upload, the average Lambda time is about 3.2 seconds. So you can scale this out. We now support up to 3,000 concurrent Lambdas if you set your limits up correct. We support 3 gig of memory and a runtime of 300 seconds. So you can do about 7 terabytes of data using MapReduce this way if you can write the query to actually query your logs, and they're quite static. The other thing is, if you were running this in production, you wouldn't necessarily upload the Lambda every time because you wouldn't actually be changing it. You'd just be running it once a day. Or if you've got a business user who wants to see something, ad hoc query, I want to query these logs and see what the ad revenue was for this particular day on this particular set of servers or this particular set of customers, you could just run this, wait 30 seconds, and you'd actually have the reduced answer that you could then grab from the results. If you're wondering how the timing on the side, it's a tool called Gnomon. You can go and download it. It's Gnomon, and you can do the same kind of thing for anything you're running from the command line. Okay, we'll switch back. So how do we build this? So the data I'm actually using is from a big data benchmark. You can use it for any of the things you're trying to benchmark. They've actually done a series of things over Hive, over Pig, over Redshift as well. And then I'm using it in our Lambda benchmark here. So it's a set of big data benchmarks that you can run any of your types of systems over and understand how they perform against all the other big data frameworks out there. So it's called AMP Labs. You can go and have a look at it. And so we've got the raw benchmark data. We are querying it through Lambda, and we're actually doing a setup function. And that setup function is really figuring out how many keys do I have, how much memory do I have, so that I can split out. And what this picture doesn't really show is when we get to the coordinator, we're actually spinning up 202 of those Lambdas in the reducer and mapper stage. So we have 1 Lambda per key actually crunching this data. So the total cost was 18 cents, and the total actual runtime was about 30 seconds with the upload. So we can do this very scalable to test out these type of functions. This is actually the code. I've just extracted some of the code and put it in the slide for you so you can have a look at what we're actually doing. We're just really pulling out the keys. We have a particular line split, so we're looking for the IP addresses. We're aggregating based on time variable. And then we have the reducer, which is actually building the Lambda and doing the reduce function. And so it's very simple code. You can do all of this in less than a couple of hundred lines of code. Most of the code is actually orchestrating, writing it to the S3 bucket, picking it up, and understanding that the job is finished. Gabe was talking before about step functions. So the reason that step functions is not included in this demo and is not orchestrating our Lambdas like you normally would is because as the size of the data changes each day, there'll be a variable number of keys. And step functions at the moment, you must actually explicitly tell it how many channels you want to map, and you must actually name them before you start. And so we couldn't do that because every time our data changes, we'd have to build an entirely new step function and upload it. So internet scale services, they're secure, they're reliable, and they're performant. But you shouldn't take Gabe and I's word for it. How about we talk to actual customers who are running this in production? So with that, I would like to introduce Dr. Matthew Berryman, and he's going to talk about Pedabencana in Jakarta.
Thanks, Shaun. So I'll briefly run through Berryman, which is a flood mapping platform operating in Indonesia, backed by MIT Urban Risk Lab, my company across the cloud, funded by USAID. So Jakarta has a number of challenges. It's sinking very rapidly under the weight of all the tall buildings and groundwater extraction. There's climate change, which leads to more intense rainfall events. There's lots of trash that gets thrown into the river and can block up the gates and pumps. And all of this leads to major flooding events in Jakarta. And we started with the observation that people were already communicating and tweeting and Facebooking about these flooding events. There are 115 million people using social media in Indonesia, and as mentioned, there's a lot of mobile use there. And this map here actually shows some data from the 2013-14 monsoon, where we just went through all of the public tweets that were there and plotted the flood locations. And in particular sections, you can even start to make out where there's lots of flooding along some of the waterways and canals there. So we decided to tap into this as a source of information and built Berryman, which is a crowdsourced flood mapping platform. It's used by the emergency authorities and they've got their own custom interface for putting in official flood height data. So I've now got a little video which demonstrates how flood information is reported into the system, and then I'll talk through the architecture. So we've got a number of bots. We've got Twitter, Telegram, and here Facebook Messenger. And I click on Get Started, and it gives me back a message inviting me to Laporkan Banjir, which means report flood. I then click on that, and I get back a custom reporting link, which then takes me to a mobile-friendly website where I can enter in the relevant flood information. Within some of the apps, they don't necessarily have location turned on, so in that case you can actually click and drag to select your location. And click on Next, and then you can click and drag to select the flood height for your area. You can upload a photo. So this was some flooding in Jakarta. Type in a description. We come to a review slide. We can go back and change any of the information if we want. And then when we're ready, we swipe to submit. And then the bot sends us a link back to our individual flood report on the map, and we can share this with our family, friends, colleagues to let them know where the flooding is. And we can view that with other flood reports and the official flood height data in the coloured regions there. So I now step you through the architecture behind this. We originally started with a monolithic app. We moved to Amazon Elastic Beanstalk for reliability and, importantly, scalability, because we can go from 10 users a day during the dry season up to 250,000 users a day during a major flooding event. And then we put API Gateway in front of that, which has allowed us to move away and start using microservices, so using Lambda for greater scalability, and also it's more cost effective. So users send that message through, that then goes through to Facebook servers, then talks to our API Gateway, which then talks to a Lambda, which is providing some of that bot functionality that we've seen. That bot Lambda then talks back through API Gateway to our core server to grab that custom reporting link, and then sends it back to the end user, as we've seen. The end user then uses CloudFront, which provides the static web content, as well as the server. And then they submit their report, and then it comes back through an SNS channel to our bot, which then sends that reply. And then we can then view it on the map. The nice thing about Lambda, as we've already seen a little bit of, is that you can get some very short pieces of code that do a lot. It's very easy to write these Lambda functions, and you really can focus on the code. You don't need to worry about a lot of the deployment aspects. And using Lambda, we've also been trying out Amazon recognition for flood scene recognition to identify where there are cars or people affected by flooding. Okay. So, head back to Shaun.